It's 4 p.m. on the clock now, so I think we're ready to start. So welcome back, everyone, to the final talk of today's session. And for this talk, we're very happy to have Professor Anatoly Dymarsky from the University of Kentucky. And he will tell us about some exciting developments in Krylov complexity in quantum field theory and beyond. So please, Professor Dymarsky, the floor is yours.
Thank you very much for inviting me, for the opportunity to speak. This is my chance to visit Korea, though not in person, but virtually, and I'm very happy about that. Today, I will be speaking about an ongoing work done in collaboration with Alex Sadoshkin and Misha Smolkin about Krylov complexity. I'm trying to understand Krylov complexity in the context of quantum field theory. Let me first give you the motivation or a broader overview of why I'm interested in this question in general. So lately, I would say during last 10-15 years, the topic of quantum chaos became very important and prominent in many different fields, areas of physics. We know that in high energy physics, quantum chaos is playing an increasingly important role, trying to understand black holes and how they behave. But in fact, this is only a small part of the story, because quantum condensed matter community and people who are trying to do quantum computers and quantum control and control individual qubits and cold atoms, they're also very interested in quantum chaos. And in fact, these are the people who reignited interest in quantum chaos something like 15 years ago. There's literally thousands of papers trying to understand quantum chaos, but quite ironically, nobody knows what it is because there is no proper definition of quantum chaos. So I want to be very specific, and I want to explain what I mean by quantum chaos and why I'm interested in this. My definition of quantum chaos, my working definition of quantum chaos, is the following. When you consider a sufficiently complex generic quantum system, it exhibits a lot of universality in its behavior. And this universality has different aspects, very different aspects of quantum dynamics exhibit universality. And whatever universal aspect you can identify, I will call this universal aspect quantum chaos. So for me, I'm not trying to give a mathematical definition, but at the level of physicists, I would say that quantum chaos is a study of universality of quantum behavior when the system is sufficiently complex and doesn't have any symmetries which would constrain this behavior. Now, in the literature, there are many different approaches to quantum chaos. One is focused on level repulsion or level statistics, energy level statistics. Another related one is the eigenstate thermalization hypothesis, which studies typicality or universal behavior of energy eigenstates of a sufficiently complex quantum system. Then you have approaches focusing on operator growth. This could be spatial growth or other types of growth. For example, behavior of out-of-time ordered correlation function, the famous ODOC, the exponential growth of ODOC, can be understood through the lens of operator growth. And more recently, in our field, after works of Lenny Susskind and in quantum computing for some longer time, people have been interested in complexity, or circuit complexity, or quantum complexity of systems. And also there are a lot of works showing that there is some universal behavior. So these are different approaches. I'm not trying to say that they're equivalent. They're overlapping. Sometimes you can have level repulsion, and from level repulsion you can see ETH, or vice versa. Sometimes you can have level repulsion but not have exponential growth of ODOC, or perhaps you can have the vice versa, exponential growth of ODOC but no level repulsion. These are overlapping properties, but they're distinct and they characterize universal aspects of quantum dynamics from different points of view. I'm interested in all of them. But when you try to develop a more uniform approach, which would be a really important question, you see that all of these distinct aspects. They're overlapping, but they're not fully universal and only apply to some particular family of systems. Let me be more specific here. Let's say I'm sticking with the most conventional sort of textbook definition of quantum chaos based on level statistics, on level repulsion. Just to define energy levels, you need a finite size of Hilbert space. For example, you need to have a system like a quantum billiard with a particle described by Schrödinger equation moving in a billiard of some shape. Then you have discrete levels, and you can define finite Hilbert space within certain energies. If you consider quantum field theory defined in flat space, it exhibits continuous spectrum to begin with, and then there is no question of level repulsion. And therefore, approaches like level repulsion, they struggle to be applied straightforwardly to quantum field theory. You first have to regularize quantum field theory by putting it in a finite size box and introduce an infrared cutoff. So this is one limitation. But then you also have AUTOC, which is defined very, very well. Just one second. I'm sorry. So then you can discuss the AUTOC, which is defined very, very well in quantum field theory, but it requires large n, and therefore applying AUTOC to the case of non-integrable spin chains doesn't make much sense because there is no large n and you cannot define exponential behavior. So you see that each approach has limitations. AUTOC is very well defined in field theory, but doesn't apply to spin chains. Spectral statistics is very well defined for spin chains, but you need to do certain things to apply to field theory. So a natural question is whether you're going to have a truly universal approach which will apply to all cases. And Krylov space, more narrowly Krylov complexity, but more generally dynamics in Krylov space, emerged a few years ago as one of the approaches which perhaps has built-in universality, because Krylov space is a very basic object which you can define for any quantum system. Now, mathematically, Krylov space is the following thing. Let's say you have a vector and you have a matrix H. So the Krylov space would be a linear combination of vectors of the form h to the power k acting on the vector. You can think of this as, in the context of quantum system, you can think of H being the Hamiltonian and V being some initial state, and then you act by Hamiltonian several times. You can act by finite number of times or infinite number of times, but usually finite number of times. You populate states Vk, and their linear combination form the Krylov space. As you see, this is a very universal thing. You can define it for any quantum system you can imagine. And in fact, there are even classical analogs. So with this built-in universality, there was a hope that Krylov complexity would provide a bridge between different aspects of chaoticity, and it would connect AUTOC, and I will talk about that. It will connect AUTOC perhaps with the operator growth of different kind, and perhaps to level repulsion and complexity and so on and so forth. So I stop here with my motivation. This is basically the set of arguments or the set of thoughts why I'm interested in this Krylov complexity business, because there was a hope, there is still a hope that this approach will be more universal and will connect different aspects of chaoticity into a more unified picture. If you have any questions, please don't hesitate to stop me and ask questions. Now I will proceed with the mathematical preliminaries of Krylov space, but I will really not go into details. My talk is really not technical. I try to brush aside all formulas and technicalities just to give you a general picture.
Excuse me. Hello.
Go ahead. Yeah, go ahead. I can hear you.
Oh, okay. So is there any case when the original vector space is infinite, but this Krylov vector space is finite?
Of course. The Krylov space is defined. You start with the initial vector, and then you act by your matrix, and you act as many times as you wish. It's up to you how many times you act. You can ask, what if I will continue acting? In certain cases, you will have to stop, because in certain cases you will exhaust all states in your Hilbert space. But then basically your Krylov space will be as large as your original Krylov space. Excuse me, as large, pretty much as large as your original Hilbert space. But in practice, you can always stop at some finite number and work with a reduced Krylov space. And in many cases, it works just as good, just as well as the full space. And that's the advantage of Krylov space, that it is finite. And this is a practical advantage. The Krylov space method was invented as a computational tool when you want to approximate highly dimensional matrices or very large matrices with much smaller matrices, which capture certain important information such as spectrum and so on and so forth. So the advantage of the Krylov space is that you can make it finite.
So for the quantum chaos, is this, should we prefer the smaller dimensional Krylov space or larger dimensional Krylov space?
We will see in a second that what people usually discuss these days are Lanczos coefficients. And to define first handful of Lanczos coefficients, you really don't need to have an infinite dimensional space. You really can cut the Krylov space finite and calculate first handful of Lanczos coefficients and see how they behave. And that will give you an idea how the system behaves. So just to give a simplistic answer to your question, it's fine to have a finite size Krylov space. Did I answer your question? Yeah.
Okay, let's go.
Okay. All right. So the starting point of this Krylov space business, not Krylov space in a mathematical sense, but very narrowly how people discuss it last few years, is the recursion method. And the recursion method starts with a two-point function. It starts with a two-point function. You can think of a more general two-point function, let's say two-point function in a ground state or two-point function in a thermal state. Throughout my talk, I will have in mind very particular thermal two-point function with a symmetric ordering. It has certain mathematical benefits, but if you want to be more general, you can think of more general two-point functions. And two-point function naturally defines a scalar product. For example, if you take beta to be 0, which means infinite temperature, and you do not always have the luxury to be able to do that. But if you schematically do that, you will have trace of two operators. And basically, the scalar product will define the norm, which is called the Frobenius norm. Even if you introduce exponents of beta h here, this two-point function still formally defines a scalar product. It's not a Frobenius scalar product, it's related to it, it's a cousin of a Frobenius scalar product, but mathematically defines as a scalar product. So once you define the two-point function, you also, here A is a quantum operator. So instead of vector V in the first slide, instead of taking vector V to be a state of a quantum system, we will do the following. Do the following modification. Let me write it down. My V0 will be an original vector. Will be an original operator A. An operator A is also a vector in a linear space of all operators. Operators can be added to each other, operators can be multiplied by a number, and therefore operators form a vector space. And my initial vector will be the operator A, and my Hamiltonian H, excuse me, I'll just go to this slide. My matrix H will be a linear operator of the adjoint action of my Hamiltonian on the operatorial space. A Hamiltonian naturally acts on any operator in the Heisenberg picture by the commutator, by the adjoint action. So this is action of H. And with this, I will define the Krylov space as follows. I will simply have the iterations like that. An plus 1 will be equal to the commutator of H with the previous step. So this is an analog, oops, I'm sorry. This is an analog Vk plus 1 is equal to H to the K V0 plus 1, which is the same as H Vk. This is the same. And then I will also add these two pieces, but these two pieces is simply to make my basis Vk orthogonal. And it will be orthogonal with respect to this scalar product. So basically what I'm doing here, I'm starting with a local operator. I'm starting with some simple operator, and I'm mathematically building the Krylov space. And while building the Krylov space, I'm simultaneously making orthogonalization. So that's all. It's a very simple, mathematically straightforward procedure. The coefficients B, which are necessary here for orthogonalization, they're called Lanczos coefficients. And I will be mostly discussing those coefficients today. For numerical methods, this recursion method or Krylov space method is very convenient because as a result, we can ask how adjoint action of the Hamiltonian will act in the basis of this vectors AK. And the matrix of this action is called the Liouvillean matrix. And this Liouvillean matrix is 3-diagonal. And since the Liouvillean matrix is 3-diagonal, and that requires a little bit of computation, but not much to see that it is 3-diagonal. But since the Liouvillean matrix is 3-diagonal, it is very easy and efficient to diagonalize this matrix numerically. And therefore, recursion method is first of all a numerical method. That's how people try to evaluate numerically time evolution. If you want to calculate the correlation function or something like that, and you need to evolve things in time, if you want to work with a Hamiltonian of a quantum system, that will be complicated. But once you build the Liouvillean, it's 3-diagonal, and you can exponentiate 3-diagonal matrix very easily. Okay, so the punchline here is the following. We start with a 2-point function C of t. And then there is a mathematical procedure, rather straightforward mathematical procedure to produce Lanczos coefficients Bn. And you see that this is the formula for the Lanczos coefficients. This is a definition, and this is a formula, meaning this is already the solution. I found the expression for this Lanczos coefficients. And you see that to calculate Lanczos coefficients, you only need to know vectors An for some. If you want to know only handful of Bn, then you only need to know handful of these vectors An. And it means that if essentially and efficiently, you can, essentially and effectively, you can keep your Krylov space finite. That goes back to the question which I was asked a few minutes ago. Okay, so you start with a 2-point function, and you can define Lanczos coefficients. That's the mathematical preliminary. If you don't have any other questions,
beta are related.
Excuse me?
How T and beta are related?
How T and delta A?
You see T. Oh, there. T is T.
T. T is time.
Yeah.
So T is time.
I'm sorry.
T is time. I simply assume the Heisenberg picture. Okay. So our next question is the following. Starting from the 2-point function, can I see the chaos of the underlying system? This is a very interesting question because normally 2-point function, in many cases, 2-point function is a very simple object which is fixed by some symmetries. For example, in conformal field theory case, it's based by symmetries or something like that. So it's absolutely not clear that 2-point function would know anything about integrability or chaos of the underlying system. But nevertheless, there is some interesting results which I want to share with you. Historically, people instead of working with two-point function, people wanted to work with the Fourier. So they calculate the Fourier transform, which they sometimes call the power spectrum. And then they wanted to study high frequency tail of the power spectrum. And it's very clear to see that the power spectrum has to go to 0 at infinity. When I say infinity, I mean that omega goes to infinity. Power spectrum has to go to 0, and you can discuss how fast it has to go to 0. And apparently, it cannot go to 0 slower than exponentially. Why is that? Because if it would go slower than exponentially to 0, once you plug, so this is a Fourier transform, you can also calculate C of t as an inverse Fourier transform, right? And if f squared would go to 0 slower than exponentially, the Fourier integral simply will diverge. And since you know that your two-point function is well defined, you can conclude right away that power spectrum cannot go to 0 slower than exponentially. If it will go exponentially, then it's very easy to see that C of t will develop a singularity, something like a pole or maybe a higher degree singularity at some finite distance away from the origin and along the imaginary axis. Okay? But then if f squared will go to 0 faster than exponentially, then C of t will be a completely finite function. It will be completely finite, it will be analytic, it will be meromorphic. For example, if your f squared goes to 0 as a Gaussian, C of t also will be a Gaussian, right? Or you can imagine that f squared will go to 0 so fast that it will become 0 at some finite value of omega. And then once you plug it back, this Fourier integral will be very easy to calculate in a sense that it will be completely analytic everywhere and so on and so forth. Okay. So this is some preliminaries about how slowly f squared can go to 0. And the slowest one is this exponential, which is the same as to say that C will have a singularity. Apparently, if f squared go to 0 exponentially, it's mathematically pretty much the same as the statement that the Lanczos coefficients will grow linearly with the index n. Well, I want to repeat the statement. I want to be a little bit more careful. Strictly speaking, mathematically, the inverse statement holds. If your Bn grow linearly, that means that your f squared goes to 0 exponentially. But if your f squared goes to 0 exponentially, that does not necessarily mean that Bn grows linearly. It only means that Bn grows linearly provided that Bn is a smooth function of index n. So this way, it's a mathematical statement. This way, it's more or less correct. Modulo possible non-smooth behavior of Bn. Okay, I'm sorry that I have to unload on you. I'm sorry that I have to unload on you those mathematical subtleties, but you will see that those subtleties will be important. Okay, let's step back. Let's take one step back and reiterate what I said. I said that f squared has to go to 0. The slowest possible decay rate is exponential, but there could be much faster decay rates. It can go super exponential, it can go as a Gaussian, it can go to 0 infinite region of omegas. Okay, fine, there's a whole zoo of behaviors. How is that related to chaos? Is it even related to chaos? We don't know, but there was some observation back in 2014 by a group of Boris Fine, who was in Germany back then and who's in Germany now. They worked with the lattice systems of classical spins. These were not quantum systems. These were lattice systems of classical spins. And they consider different models, both integrable and non-integrable. and non-integrable models were chaotic, and they saw that explicitly because there's a classical systems, and the definition of chaos is well defined for classical systems. And they noticed that whenever a system is integrable, power spectrum decays faster than exponential. But when the system is not integrable and chaotic, power spectrum decays exponentially, meaning with the slowest possible rate possible. With the slowest rate possible. So back in 2014, they outlined the following observation. Exponential decay, slowest possible decay of power spectrum is a signature of classical chaos. Okay? We don't know an underlying reason for that, but that's an observation. More recently, in 2020, we had a paper with Alex Avdoshkin. This is the paper I had in mind. And then we had a follow-up with Alexander Gorsky discussing this picture in a little bit more detail when we made the following straightforward observation. If you now go to quantum lattice systems and you say that your power spectrum decays exponentially, mathematically, you can immediately see it means that your function C develops a pole along the imaginary axis. And if you remember that C was something like trace of A, the fact that C develops a singularity means that the norm of your operator A along imaginary axis means that you evolved your operators along Euclidean time. It means that your norm of your operator evolved in Euclidean time diverges. And we saw very clearly that this divergence, it's not anything surprising or exotic, but in fact, when you try to calculate the norm, I need maybe a little bit of space. When you try to calculate the norm of an operator like this, I'm writing here Euclidean time evolution. If you try to calculate the norm of operator like this, you need to calculate the norm of nested commutators, right? Because you can expand on Taylor series. Once you start calculating norm of nested commutators, you will see that there are on a lattice, you will see there are different geometries of lattices will contribute. And there is a universal bound coming from the geometry of lattices. And we saw that these bounds themselves diverge. So basically, we saw in 2020, relatively recently, a few years ago, that this behavior outlined by Boris Fine, that this behavior is completely consistent with the following simple qualitative behavior, that the norm of operators grows as fast as it could, subject to some universal geometrical constraints imposed by the lattice. So there are certain kinematic, if you wish, constraints, which are there because you have a lattice system, but the operator grows in a chaotic non-integrable case, it grows as fast as it can, subject to some global kinematic constraints. So in that sense, this is a very, very simple and intuitive picture. Okay, I'm jumping over some important work here because our work was 2020. It was posted to arXiv 2019, but it appeared in print in 2020. But before that, there was a very important pioneering work by the Berkeley group, Parker, Cow, Avdoshkin, Scafidi, and Altman. And this is 2019. It appeared on arXiv in 2018, which formulated universal operator growth hypothesis. Their universal growth hypothesis is the following. They say that in a typical non-integrable system, Lanczos coefficients grow linearly. And as we saw on the previous slide, this is essentially mathematically equivalent to saying that f squared grows exponentially, decays, not grows, decays exponentially. So they took the observation by Fine and his collaborators and extended this observation to the quantum domain, reformulated it in terms of Lanczos coefficients and said, this is a universal property of quantum systems. So our work of 2020 of reformulating this in terms of nested commutators was essentially a follow-up. We already knew about this work by Altman and collaborators, and our goal was to better understand the origin of this universal operator growth hypothesis. Besides just introducing Lanczos coefficients as a potential probe of chaos, they also introduced the notion of Krylov complexity. And Krylov complexity is defined as follows. Through this recursion method, you define vectors an in the space of operators. Then your original operator evolved in time can be expanded in this Krylov basis. And then with proper normalization, vector Cn is normalized. So sum over n Cn squared is equal to 1. And then Krylov complexity is a time-dependent quantity, which simply counts the typical or average index in the Krylov basis to which your operator has grown. I do not know if my explanation is clear, but I'm just trying to say that you have a basis A0, A1, blah, 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 AK, and then your operator as a function of T is a linear combination of this A guys with the coefficient C. And then the Krylov complexity is a function of time defined this way. And Cn coefficients can be thought of as some sort of efficient wave function. So this Krylov guy is simply the average value of the index. Okay. And okay, so what this Berkeley group understood is that if your Lanczos coefficients grow linearly, which means that the power spectrum goes to 0 exponentially, it basically means that the Krylov complexity will grow exponentially. And they conjectured right away that the exponent of the Krylov complexity will bound the exponent of out-of-time order correlator. This is an important formula. Lambda autoc is bounded by lambda Krylov. This is the conjecture, a highly non-trivial conjecture, which they put forward in 2018, and they proved this conjecture for infinite temperature. And more recently, there was progress proving that for finite temperatures. And that I think, let me emphasize this, that I think is one of the most interesting things about Krylov complexity, that it immediately connects conventional definitions of chaos, like the definition of chaos which Boris Fine worked with. So there is some obvious connection to those works, conventional definitions of chaos, and it also connects to behavior of out-of-time order correlation function. So this universal aspect of Krylov complexity, that it connects different aspects of chaos, I think is the most important and most interesting thing about it. Okay, I'm not sure.
Can I ask you a question?
Yes, yes, of course.
So lambda OTOC is information of the 4-point function. And while if I am understanding correctly, lambda Krylov is information of a 2-point function.
Yes.
So do you think that both of them contains the equal amount of information, or one is more important than the other?
I don't think they contain the same information. I don't think this is true. In my paper with Misha Smolkin, which was mentioned before the talk, I sort of asked questions along the same line like you did. I said, lambda autoc is a property of 4-point function. Lambda Krylov is a property of 2-point function. How is that even possible that one bounds the other? But it's probably not completely impossible to understand how 2-point function can bound 4-point function, because there are some kinematic constraints. 4-point function is sort of a, you can think of it as some disconnected piece consisting of 2-point function plus some connected piece and so on and so forth. And you can imagine that once you add more and more connected pieces, the inequality will go in one direction. So lambda auroch will become smaller than Krylov, lambda Krylov, and one bounds the other. So it's, I'm not trying to say that I gave you a proper explanation. I'm just trying to convince you that it's perhaps not completely crazy to think that one can bound the other. But I don't think at all that they have equal amount of information. I think lambda Krylov is sort of simpler object, perhaps more universal. And the fact that it bounds something means, in my view, that it has less refined information. And I think lambda auroch is a more sensitive probe. And I think it has more information because it knows about 4-point function, and 4-point function sort of has to know something about 2-point function as well, but not the other way around.
I see. So then, do you think that there might be some example where 2-point function is going like an exponential, while OTO, I mean 4-point function is not like an exponential?
I'll give you an example.
Oh, great. Thank you very much.
Yes. I'll give you an example. This inequality sometimes is non-trivial. Sometimes it is saturated that they're equal. Sometimes it is trivial in the sense that right-hand side is non-zero and left-hand side is 0, because lambda auroch cannot be defined. There is no exponential growth of auroch. So if there is no exponential growth of auroch, I will simply say that lambda auroch is 0. And there are plenty of examples like that. Let me try to speed up a little bit. I was mentioning earlier that equivalence between exponential decay of this and linear growth of this is mathematical equivalence up to subtleties. There is a mathematical example, or rather counterexample, in our paper with Alex Avdoshkin, where you can have a sequence of Bn which are not smooth. They split into 2 branches. One branch grows, this is not Bn, this is Bn squared. I do not know if you can see it clearly. This is Bn squared. So one branch grows like a linear function. Here it's shown as a parabola. This is n squared. And another one is growing as a square root. So it's n. In this case, f squared grows with the, f squared decays with the slowest possible rate, but it doesn't translate into linear growth of Bn because they're not smooth. So just keep in mind that mathematically there could be some subtleties. Okay, so now I want to give you just 1 second. I apologize. I'm sitting on the street, and sometimes there are some disturbances. Okay, so my time is running fast. So let me quickly mention that universal operator growth hypothesis is formulated in a constrained or sober way. It simply says that a typical quantum system will exhibit slowest possible decay of f squared, or equivalently fastest possible growth of Bn. There is no statement that it will be sensitive to chaos or integrability, in a sense that every single instance of integrability you will be able to probe with the growth of Lanch's coefficients. They never said that in their paper. But of course, it's very tempting to make the statement stronger and say, can I use growth of Lanch's coefficients as a probe of chaos? And surprisingly or not surprisingly, but people saw a lot of success doing that. So the original paper by Berkeley group, they saw that in the SYK model, you have the maximal growth of Lanch's coefficients because SYK is chaotic. Then there is a 2-dimensional lattice example, which you can use. It's an early lattice example, which you can use to also see that for chaotic lattice, 2-dimensional lattice, you can have maximal growth of Lanch's coefficients. The same thing was recently understood by Cao for 1-dimensional non-integrable Eisen model. So in all cases, when you have chaos, you have universal maximal growth of Lanczos coefficients. But the contrary statement is also true. When people consider integrable spin chain models, they saw that the power spectrum goes to zero faster than faster than exponential, faster than the slowest rate possible. And perhaps the most striking non-trivial example is given by numerical evidence. It's not 100% ironclad evidence because it's numerical evidence, but it's a complicated numerical calculation in the XXZ model. And the authors of this paper claim that they see that the power spectrum goes to zero faster than the slowest rate possible. In one dimensions, the slowest rate possible is not exponential. I'll just quickly go into that. In one dimension, the slowest rate possible has to be faster than exponential. It has to be like this, but they claim that they see exponential. At least that's what they claim in person when I talked to Marcus Riegel, who is one of the authors. So I'm an optimist. I will give them the credit by saying that they indeed see the exponential behavior, although it's still an open question to prove that analytically. But if that's the case, the punchline here is the following. Not only universal operator growth hypothesis is true, but also Lanczos coefficients is a sensitive probe of chaos and can be used to see chaos quite clearly. Excuse me. Okay, so now.
Sorry, can I make a quick observation?
Yes,
it seems it seems that a common feature of the models that you showed before is that they are lattice models. So in some sense, some finite dimensional models, right?
Yes. Rather, yes, they're lattice models, but what other models you had in mind, like field theory models?
Yes.
Good. So let me start talking about field theory models. I have 20 minutes and my main talk should be about field theory models. I'm skipping this part about this. This already told you that lambda autoc is bounded by lambda Krylov, but this is a conjecture. So this is just a repetition. I had a slide showing some progress. Let me just quickly go over this slide. So I told you that this inequality was proven in the original paper by Parker et al. For zero temperature. We reformulated this inequality in a slightly more beautiful way, if you wish, or simpler way, not beautiful, but mathematically more transparent way by invoking the singularity of two-point function. And in this form, it's not a universal statement, it's a statement that assumes smoothness of Bn. So this statement assumes smoothness of Bn, but with this implicit assumption, the statement in this form was very recently proven by Gu, Kitaev, and Zhang. Okay, it was proven by Gu, Kitaev, and Zhang, and that gives credibility to this. And moreover, once you look into this, let me make the following transition. Once you look into this, B0 is a non-negative constant. Well, it's a non-negative function of beta. It's automatically bounded by 2 pi over beta. And therefore, we now conjecture, sorry, I'm jumping a little bit. I have discontinuation in my story, but let me give you an intermediate punchline. The inequality between lambda autoc and lambda Krylov, we conjecture to be extended to some generalization of the Maldacena-Stanford-Shanker bound. You very well know that lambda autoc being smaller than this is a Maldacena-Stanford-Shanker bound, but basically we are trying to say, here in our 2020 paper and in our upcoming paper, that the relation between lambda autoc and lambda Krylov should be understood in the context and as a generalization of Maldacena-Stanford-Shanker bound. This is a formula which we want really to prove. And in some context, with some additional assumptions, it was recently proven by Gu, Kitaev, and Zhang. Okay, but you can still say that this is all about discrete systems. And what about field theory? With the field theory, the story initially seems to be very simple, but boring and uninteresting. Because in field theory, we can discuss two-point function. It's a thermal two-point function. You can think of it as a field theory on a cylinder with a circumference beta. The S1 has length beta. You put two operators in the opposite sides because of the ordering here. And you know very well that when you start doing time evolution, if you move into Euclidean domain and one operator will start going into another operator, the operators will collide. And once they start colliding, you will have a UV singularity of a two-point function. Once you have a singularity of a two-point function, you immediately recognize that this is the singularity of C of t I was mentioning before. And from here, you immediately see that in quantum field theory, doesn't matter what kind of quantum field theory it is, f squared of omega always decays exponentially. Always. It's a kinematic statement, which is just a result of the statement that two operators, when collide, there is a singularity. So it's some strange story because it doesn't matter whether your quantum field theory is integrable or not. It could be free. It could be integrable with some non-trivial symmetries. It could be completely chaotic. It could be holographic. Two operators collide, you have singularity. Once you have singularity, you have to have slowest possible decay of the power spectrum. And therefore, you most likely will have linear growth of Lanczos coefficients unless, and I want to stress that, unless you have some exotic behavior when, for example, Lanczos coefficients split into different branches. I have shown you the picture where Bn was split into different branches. But unless you have this exotic behavior, you have a very plain standard story when Lanczos coefficients are not sensitive to chaos. So 1 year ago, like in last spring with Misha Smolkin, we wanted to understand what's going on in field theory. We saw that unless a miracle happens, Lanczos coefficients will not be sensitive to chaos. Moreover, the relation between lambda autarch and lambda k will become very simple in this case because it will simply reduce all the Stanford Schenker bound. Okay? And let me make this story, long story short. A year ago, we calculated Lanczos coefficients for many different models of CFTs. We consider two-dimensional CFTs when two-point function is given by kinematic constraints. It just by Virasoro symmetry, whatever, conformal symmetry. We considered free fields in various dimensions. And in all cases, Lanczos coefficients, they might split into two branches, but these are not two branches with different slopes. These are two branches which come very close to each other. And therefore, just to make, and we also consider holographic examples. Also, you have two branches with the same slope. Those two branches come close to each other. So basically, to make the story short, what we saw a year ago is that no miracle happens. All the charms, all the miracle properties or good properties of Lanczos coefficients as a probe of chaos, not applicable in field theory. You can still claim that the universal operator growth hypothesis holds, but in a more restrained form, that typically you have linear growth. But here, it's not typical. You always have linear growth. Excuse me, I had some background noise and I decided to mute myself for a second. So it's an unfortunate situation that in field theory, the result seems to be disappointing. There is no non-trivial statement. You always have linear growth of Lanczos coefficients. So that was a year ago, and it was only for conformal field theories. You can ask what happens if you add mass. Mass really doesn't change things much, but we really wanted to understand why this is happening. And I think 1 year down the road, we understand a little bit better. So this is the upshot of the field theory or CFT, or maybe field theory more generally. No miracle happens, Bn is smooth because you have singularity of two-point function in the complex plane. Bn always grow linearly. Moreover, I will tell you the asymptotic, not only the linear piece, but also the constant piece. The constant piece is completely fixed. by the dimension of the operators. Whether you have CFT or not, when two operators collide, you can effectively describe them in the UV CFT, and the delta is the dimension of those operators in the UV CFT. So you have the asymptotic behavior of the Lanczos coefficients, which is just linear. You have the Krylov complexity, which grows exponentially. It trivially bounds lambda autarch because it simply becomes the Maldacena-Stanford-Schenker bound. It all makes sense, it all works, but there is no non-trivial information here. There's no probe of chaos coming from Lanczos coefficients or Krylov complexity. We wanted to understand why this is happening. I believe we understand why this is happening. So I want to spend 5 minutes explaining why this is happening. Any questions? I think this is happening because of the locality and Heisenberg uncertainty principle. I will try to build an intuitive picture. I will have to skip some mathematics, but I'll try to build an intuitive picture. You can try to be more rigorous here, but intuitively, I've squared the power spectrum of the two-point function in physical terms. It can be thought of as an amplitude, a transition amplitude between two states of one particle. You have a quantum mechanical particle. Forget about quantum field theory. Think about a photon or an electron as a single quantized, in a single quantized terms. You have a quantum particle. It has states. It has state with the initial energy. It has state with the final energy. And the distance between initial and final energy is omega. F squared of omega is roughly the transition amplitude between those two states. If you have a local operator to begin with, it basically means, at the qualitative terms, that you're considering a particle which is initially in a localized state. The wave function of that state is a delta function. If you know the location of your particle exactly, Heisenberg uncertainty principle tells you that you don't know the momentum. The Fourier transform of a delta function is a constant. It means that the transition amplitude from the delta function localized state to the plane wave of arbitrarily large energy is completely unsuppressed. There is exactly the same amplitude, transition amplitude, from the localized state to the plane wave with short wavelength or to the plane wave with a long wavelength. Once you introduce certain kinematic parameters, this constant transition amplitude develops this exponential factor minus beta omega. And what I'm trying basically to say that this exponential decay of F squared, excuse me. This exponential decay of F squared in field theory, in simple physical terms, is simply a consequence of locality of your operator, because you're trying to discuss the transition amplitude of a particle from the localized state into plane waves of arbitrarily high energy. And you can be more specific about it. You can consider a quantum mechanical particle, first quantized, described by a free Hamiltonian. As an operator, you consider an operator of this form. This is a Heisenberg picture. So A should be understood as a quantum operator. And then parameter small a will control the size of your wave packet. If small a is very, very small, you localize your initial wave packet. If a is very, very large, then your wave packet is very, very large. With this setup, you can calculate power spectrum exactly. Function k0 of x goes like e minus x. So you can simply think of this as being e minus of this argument. And you see very clearly that if your initial wave packet is localized, a small is equal to 0, you will have exactly universal tail like this. But if your initial wave packet was delocalized, capital A is very, very large, it means that we will have much faster decay. Okay, so this example teaches you that if you start with a delocalized initial state, you will have much faster decay of the power spectrum. But if your initial state was localized, you will have the slowest possible decay of a power spectrum. Okay, so this is the intuition. I understand that I should probably spend more time building this intuition, but I don't have time for that. This is the intuition. But if this intuition is correct, let's see what will be the consequence of this intuition. Let's go back to field theory, but let's now think of field theory as a low energy limit of some lattice system. Imagine I have a crystalline lattice with some lattice spacing, which is a UV cutoff. And if I go in energies well below that, I will have continuous quantum field theory. And there I will have localized particles. But if I go to energies around the cutoff, I will again see the lattice and nothing will be localized. If this picture is correct, it means that if I started with the lattice and take temperature to be very, very small, I will not see the lattice to begin with. I will see continuous quantum field theory. And in the continuous quantum field theory, according to these arguments, I will have this universal behavior of the power spectrum, and I will have linear growth of Lanczos coefficients. But once I probe the UV regime, things become more interesting. And in this UV regime, I should see the lattice structure, and then I should be able to use the original story, which I told you in the beginning of my talk today, and Lanczos coefficients should be really sensitive to chaos. This is already a nuanced, non-trivial picture, and I can check it. I can check it in the simplest model of discretized oscillators on a lattice. This is the simplest model possible of bosons on a one-dimensional lattice. In the long wave limit, it of course becomes free field theory. But once you increase your energy and you see the lattice spacing, it becomes a lattice model. In this model, you can calculate behavior of Lanczos coefficients, and you see very clearly that it first exhibits linear growth, but once it touches UV regime, it goes in this case to a constant because this is a free model. And in a free model of this kind, Lanczos coefficients exhibit constant behavior. This is a well-known thing. So basically, it means that this is a QFT regime. And in this QFT regime, Lanczos coefficients don't know anything about chaos. They're sort of kinematically fixed. But in this regime, which is truly asymptotic regime, Bn are sensitive to chaos. Going back to field theory and our failure to use Lanczos coefficients to probe chaos, I should look at this from the different angle. I should say, look, field theory by itself is not a complete story. I should always think of a field theory as being embedded into some lattice system to be a low energy limit of a lattice system. The linear growth of the Lanczos coefficients, which I observe in the quantum field theory, is not the asymptotic behavior. It's an intermediate behavior, which will sooner or later change once I hit the UV cutoff. And the true asymptotic behavior after I hit the UV cutoff, that behavior will tell me whether my underlying lattice model is chaotic or integrable. So that's the picture we have for the quantum field theory. If you don't want to play this game, if you say that your quantum field theory is renormalizable, it means that you're pushing this point to the right more and more. And basically it means you never see the true asymptotic regime because the only regime you see is the linear growth, which continues perpetually. And you think that this is asymptotic growth, but from the more physical point of view, you should always think of it as an intermediate regime. And unless you hit the UV cutoff, you never see the true asymptotic regime. Now, this is one model where we see this behavior. You can play the same game with the integrable spin chain. If you have a spin chain, and we already saw Altman and friends in the original paper, other people studied Lanczos coefficients as the probe of chaoticity in spin chain, and they saw that this works very, very well, but they did it at infinite temperature where you probe the UV cutoff right away. We saw
excuse
that
me.
take the temperature. Yes.
Oh, Could you just repeat the your statement that is the asymptotic behavior of Bn is probing integrability and the chaos. In what case it gives integrability and in what case it gives chaos? Could you repeat?
Yes, yes. So Bn growing linearly. So this is chaos. It's a traditional dictionary. I'm not telling you this is how it is. I'm just telling you.
But that is not asymptotic, right? Right.
Again,
but that is not what you want to say, right?
No. This is. Well, let me first tell you the dictionary. Then Bn grows slower. This is integrability. People saw this dictionary working in lattice systems. I was trying to give you some evidence, including XXZ model. People saw this dictionary working in lattice systems. What I'm trying to say is that in field theory, you will always have linear growth, which is kinematically fixed. It's fixed by locality of the system. And this growth will persist until you hit UV regime. If you have a UV regime, if you have renormalizable field theory, you should think of it as a theory with the infinite UV cutoff. But for the sake of an argument, let's make large but finite UV cutoff. So linear growth before you hit UV regime is not an indication of integrability or chaos. I was trying to argue that this is fully fixed by locality, by Heisenberg principle. It has nothing to do with the Hamiltonian of your physical system. But once you hit UV regime, this behavior, which I will call truly asymptotic behavior, I hope, and there is a reason to hope, that this asymptotic behavior will be sensitive to integrability or chaos of the underlying lattice system. I'm always thinking of my quantum field theory as a low energy limit of some lattice system. So for this asymptotic regime, this dictionary presumably should apply. In this picture, in this slide, it certainly applies. This is a free model and constant behavior of Bn. Constant is slower than linear, and that signals integrability. So there is total match. There is no problem.
I see. Thank you very much.
Okay. I also was trying to say,
sorry,
you can play this.
Let me interrupt you for a second. Just in view of time, since we're already at 5 p.m., maybe we can give you 5 to 10 minutes to complete the story. And
I see that I ran over time, so I'm in the regime of very quickly wrapping up. First of all, this 35 slides is not correct. I have, I think, 23 overall, but I will start skipping over slides. No, don't worry. I'm in the regime of wrapping up.
Okay.
I was also trying to say that the same picture, you can verify the same picture with the spin chains. People had success applying this dictionary to spin chains, for example, XXZ spin chains, Eisen spin chain, and so on and so forth. But they would consider something like this. And this is a two-point function associated with infinite temperature. And infinite temperature probes UV regime right away, if you wish. But if you consider the same integrable spin chains at very small temperature, then presumably you should first see long wave dynamics, which will be described by the effective quantum field theory. And there you should see some linear growth. And indeed, for spin chains, you have initially linear growth, and then this linear growth changes into square root of n. Here you have n, and here you have square root of n. This square root of n is a signal of integrability of the underlying spin chain, but you don't see this integrability before you hit certain UV regime. So hopefully this other picture will be in our paper. But qualitatively, it's very similar. First, you have linear, and that's not a signature of chaos, then you have a transition. So the punchline is that unfortunately or luckily, I cannot save Bn as a signature of chaos in case of quantum field theory. But now I understand why. This is because quantum field theory better be thought as a low energy limit of some lattice system. And what I thought was an asymptotic regime is only an intermediate regime. And the asymptotic regime emerges when you start probing UV region, UV physics. Okay, so I have a comment about Krylov complexity not exactly matching the holographic complexity. I will skip about that. The last thing I wanted to say, I just literally need maybe 2 minutes to do that. You can also play the game of trying to introduce the infrared cutoff and placing your field theory on a sphere. So this is a thermal sphere, but you can also put your quantum field theory on a spatial sphere. And in this case, we see a very exotic behavior that instead of one line of Lanczos coefficients, you have two straight lines. Bn goes like alpha n when n is even, and Bn goes like alpha prime n when n is odd. This is a truly exotic behavior we never saw before in any physical system, but here you see this behavior. It's up to you what to make it, whether it contradicts universal operator growth hypothesis or not. If you formulate the hypothesis in a conservative way, that this is a typical behavior, then it doesn't contradict this hypothesis because this is a very particular free massless scalar. Once you start deforming the scalar, those two branches will join again, okay? But what I wanted to say is that since you have two branches, you can ask the question, does it really affect the statement lambda Audoc is smaller than lambda Krylov? It doesn't, because lambda Krylov in this case is finite, but lambda Audoc is 0. This is a free field theory. There is no lambda Audoc. This statement is trivially true. But then there is another statement which used to be trivially true in field theory, but now it becomes highly non-trivial. In this case, this statement becomes highly non-trivial because you still have linear growth, but this linear growth splits into two branches, and you need to reanalyze things from the scratch. And we did this analysis. We understood that if you have two branches, Krylov complexity grows exponentially, but this exponent, to show that this exponent is always bounded by 2 pi over beta, we have to develop the whole formalism of integrals over D paths. So mathematically, this is a highly non-trivial calculation. I'm skipping all of details. I'm out of time and I have no interest to tell you all the mathematical details. But the punchline is the following. After rather non-trivial mathematical work, we were able to show that lambda Krylov in this case is bounded by 2 pi over beta. And that gives additional confidence that this double inequality is a universal thing, okay? All right, I know that my talk was consistent of a bunch of, it's a mosaic, it's a bunch of similar and related statements. And unfortunately, that's how this field works. You have a bunch of unrelated statements. So I have the last slide where I will try to bring things together, okay? The main thing we understood during last year is that if you have a system which has continuous description and some limit, for example, it's a spin system, it's a lattice system, but you consider low energy, long wave limit, because of the locality, because of the Heisenberg uncertainty principle, you are guaranteed to have linear growth of Bn coefficients. But you should always regard this linear growth of Bn as an intermediate regime. And you will, if you're interested in underlying chaos, you need to wait until your Bn start probing UV physics and the discrete structure. And only then you can hope to see truly asymptotic behavior. And only then you may use behavior of Bn as a probe of chaos. This is a punchline number 1. The punchline number 2 is that we are proposing a hybrid, a generalization of Maldacena-Stanford-Schenker bound joined together with the inequality between Krylov complexity and AUTOC. And this bound has been proven in some scenarios, and there are some non-trivial checks. There is no universal proof. Sometimes this inequality is non-trivial while this is trivial, and sometimes the other way around. We don't have a full proof, but we propose this as a fully universal statement, which generalizes Maldacena-Stanford-Schenker bound. And the third statement, which I'm hesitant to say much about because I didn't cover it in my talk, is that comparing Krylov complexity with the holographic complexity, we don't really see much similarity, but it's perhaps a little bit premature to draw any conclusions about that. So I will conclude with those two things, which I was trying to convey today. Thank you very much.
Okay. And thank you very much, Professor Dymarsky, for the very interesting talk. I wish we had more time, but fortunately, we have some time for a few questions. So if there's anybody who would like to start.
Okay. I have one question. Did one check the lattice-Wilson fermion field and still get a similar result to the lattice bosonic field?
Yes. So for the we are talking about this one, right?
Yes.
You can have different spin chains. If it's an integrable spin chain and you consider infinite aperture, depending if it's a non-interacting fermions, then Bn will be a constant. That's known, people check that. If Bn are sort of like interacting, then Bn will go like square root of n. Okay?
For
That's the
spin chain,
expectation. Yeah.
I just say for spin chain I can expect, but if I consider the lattice-Wilson fermion field.
If you consider what lattice?
Lattice-Wilson formulation.
Yeah, it's a lattice formulation. It's a spin chain formulation.
Another to say
let's
spin
say-
chain. I say I put the fermion field on the lattice and use the Wilson formulation. And at the time that you will break the chiosymmetry. So
you
even-
want to have a continuous. You want to have something like psi of xt and put that on the lattice.
Yeah. But I would say Wilson fermion field theory, because at the time, even if you take a continuum limit, Lagrange cannot have the chiosymmetry, but you can. But sometimes we expect that if you calculate the physical observable, you can have the still enjoying the chiosymmetry.
Yeah, I'm not sure what is the aspect you're interested in. So you want to have
Okay, maybe let me say
you want to have anti-commutant fermions, but you want
because
to
the
put them on
lattice theory usually have some issue about the continuum limit. So I just want to consider the one
Right.
system, but the symmetry was broken by the even for continuum limit, you still do not have the symmetry. Then do we still have some universal behavior as you demonstrate?
Right. I will be honest. I never thought about putting genuine fermions on the lattice. What I thought about is the spin chains, which become fermions in a continuous limit.
Okay.
That's what I thought. For example, you can have Eisen model in a transverse field, and that will become free fermions in the particular limit, right? In the critical point.
Okay.
So
maybe
that's the more.
I just say maybe my concern is that usually we can use the different lattice formation to study lattice theory, but sometimes different lattice formation will give the different result if you do not careful about the continuum limit. So I just wonder whether this result is also universal. Yeah.
Well, that's I think I know the answer to this question. Let's consider two lattices which have the same infrared field theory description, but as lattices they're different. It means that this regime will be the same, but then once you hit UV, you will have different behavior. Right? And
Yeah,
let's say you have two lattices. One is integrable and one is non-integrable, but they have exactly the same infrared field theory description. Then this one will continue linearly and this one will continue sublinearly. That's completely possible. And this behavior will be completely universal. It's a field theory behavior which has nothing to do with the UV because it's well below the UV scale.
Okay. Thank you.
Yeah, I have a question. Could you explain why do you associate large N with UV? Because I think of N as some sort of time, and usually large time is associated to hydrodynamic behavior or like infrared physics. But here you have like the opposite going on.
Yeah, well, one easiest way to see why BN can be associated with energy is because BN have dimension of energy. Remember, it was HA minus B squared A is equal to AN plus 1. So B squared has to have dimension of energy. And normally BN goes like N over beta, where beta is temperature. So this is a dimensionful quantity. And once you hit here, it's 1 because it's all numerical, but this is basically UV scale.
Oh, I see.
If your B grow, once they become of the UV scale, that's when you have to know about UV physics.
I see, thanks.
Yeah, but I mean, energy is related to time, so it's not completely crazy that. But large energy, you would normally say it's a very short time. Here, it's not exactly the same, right? You start somewhere here and you propagate. Yes, that intuition doesn't really work.
Yeah, I was thinking only about N, but like I didn't notice like B had dimensions of energy. So
yeah,
I think that's a good motivation.
It has dimension. But yeah, larger N means that you commuted the operator with Hamiltonian more times. So you can think of growing the operator to larger. If you write this commutator in the energy eigenbasis, then it will be AKL E minus EK minus EL, right? Or yeah. Sorry. HA many times nested commutator KL is equal to EK minus EL to some power. Let's say M times AKL. More times you commuted, more power you have here, and that's how you can reach high energies.
Oh, I see.
Do we have more questions? Maybe I can ask one final one related to your comment about Krylov complexity in holography. If I remember correctly, there was a paper by Swingle a few years ago, maybe, where he was studying basically Krylov complexity like in the SYK, and he was making some connection to JT gravity. And if I remember correctly, he did show that some qualitative agreement between the holographic expectation and the Krylov complexity in the SYK. But now you mentioned that there doesn't seem to be some good agreement.
Yes.
Could you maybe just mention this?
Yeah, right. So there was a paper 2020 by Brian Swingle. There was a number of papers by Eliezer Rabinovich who collaborated on this, I think with different people, the same group of people, but maybe not the same group of authors in every single paper. I think Ruth Scheer and Julian Sonner, maybe someone else. I'm sorry if I don't remember all collaborators. But those both groups of authors, they considered SYK model, and I think in papers by Rabinovich, they also considered something like spin chains. Excuse me. excuse me, there is a car passing by or something like that. So they consider SYK model, they consider maybe some spin chains, and they saw some similarities. And I don't want to say that anything is wrong with those papers, but all of these cases are for finite dimensional systems. When I was saying that things don't quite work well, I was saying that my preliminary analysis for field theories shows the following. This intermediate regime, which can persist for very, very long time if you make UV very, very large, this regime doesn't know about chaos, and at the level of growth of K complexity, it doesn't match holography at all, because in this regime, K complexity grows exponentially, and holographic complexity should grow linearly. So they claim that linear growth will occur in this regime, but whether it will occur or will not occur depends on the UV completion. And this is something I'm thinking about right now, because the answer is not clear to me if you can make any interesting or universal statement. What is clear to me is that while you are in the domain of field theory, while you're governed by the field theory, you will have exponential growth of K, and it has nothing to do with holographic complexity. It doesn't look like holographic complexity. And then you have non-universal regime. It's non-universal because you can have very, very different UV completions of the same field theory. And maybe there will be completions which will match holographic complexity, but if there is only one such completion, but others don't match, I'm not sure what kind of statement you want to make, right?
I see.
I'm not dismissing their papers, and certainly not trying to say that something is technically wrong with those papers. Certainly not saying anything like that. It's just that they consider finite dimensional systems like SYK, and I don't understand how to properly think about field theory in this context, because my understanding is that field theory should be embedded in a finite dimensional system, in a lattice system, but I'm not yet ready to say if there is some universality about once you do that. Okay.
Okay.
But clearly this regime has nothing to do with holographic complexity.
Right.
That I can say. But I think they agree with that, because it's characterized by exponential growth of K, and that's not what you expect. You expect linear growth from holography.
Right.
That's all I know at the moment. But you see my sort of point of confusion, right?
Right. Yes. Yeah. I understand. Thank you.
Okay.
More questions? I don't see anyone else. So let's thank the speaker again.
Thank you. Thank you very much.
Thank you for the very interesting talk. And well, hopefully we can discuss things further at some point.
Absolutely, yes. Do you want me to stay online now to discuss, or this is a statement?
Yeah, maybe I want to ask a few more questions, maybe off the record.
I'm happy to stick in. Yeah, sure.
Okay, thank you.